So I'm Nicole, and slight recap, I work with Tom Mitchell on neuroimaging data sets. If you're interested in that, come talk to me. And today I'm going to talk about maximum likelihood estimation, maximum a posteriori, and the bag of words model. So let's start talking about machine learning for text analysis. We've been working with these kind of toy data sets, these features that are discrete properties of things or numbers of some kind, right? But how can we decompose a body of text into something that we can give to a classifier so that a classifier can work with it? So for example, if we want to analyze tweets, so here's a tweet. Let's say I have some task where I want to know if a tweet came from this source or some other source. There's kind of a lot of things to worry about, right? There's like the actual words in the tweet, but there's also the grammar that's going on. There are a lot, language is pretty complicated. So how can I summarize these things in such a way that I can pop it into some naive Bayes classifier, for example, and do something useful with it? Bag of words. Does anyone have an idea of what that means? Like what we might do to this tweet to make it into a bag of words? Anybody?
Best characterizes that tweet without redundant information.
So the best set of words to characterize that tweet without redundant information. Okay, that's more sophisticated than a bag of words. Something like the simplest thing I could do. Sorry, repeat that? Right, the order of the words, right. So I could say I don't care about grammar at all. I just care about the words. Take all of the words. I only put some of them in this little cartoon, but take all the words in the tweet and just consider them separately. I don't care about their order. I don't care about what their role is. I just take all the words. So that is the bag of words model. How can we use this in classification? So recall, in class already went through what you do for discrete naive Bayes, right? Your training data are these pairs. You got your X, you got your Y. In our case, X is going to be the set of words in no particular order, as someone said. And our Y might be, who the tweeter was or something. So to calculate our prior, we would count up all the times in our training set that this tweeter shows up. And to get our data likelihood, what we're going to do is just get the conjunction of these words occurring and the class being the class in question. So it's actually very simple, right? The bag of words allows us to ignore all the complexities of language, pretty much, and just do naive Bayes kind of how we would. Are there any questions on that? No? OK. So let's get into maximum likelihood estimation. What are we trying to do when we classify things? What's the goal? Anyone? Anything? Pardon? Right, so get the predicted class for the feature. So what is it about that class? We want the class that is what, given the data set? Most likely, that's right, most likely. Right, and if we Bayes rule it, we want the class assignment that makes the data we have the most likely. Hence, maximum likelihood. So this is, as you recall, this is the likelihood. Here's the prior. We want to maximize the likelihood. And this will hopefully lead us to an optimal classifier. Not a perfect one, but an optimal one. So more simply, we sometimes just want parameters that will make the data the most likely. Maximum likelihood estimation is something that's used in statistics, and that's like where it comes from. So I'm going to go through an example that for those of you who've taken statistics will be somewhat of a review, but of how we actually do maximum likelihood estimation. So I've got these data points, and I suspect that they come from a Gaussian distribution. And I want to know what the mean and the variance of that distribution are. Recall from last recitation, here's the PDF of a Gaussian. So the probability that one of these data points has its value is given by this function. And I've got n of these data points, and they're IID. Can someone tell me what IID means? Thank you. Independent, identically distributed. So independent, I got each data point by itself without any effect from the others. And presumably, they come from the same Gaussian, because otherwise, why would I do this? So that allows me to write the likelihood of the data as a product over my n points. And I want to find my parameters by maximizing this quantity. But as you can see, this is pretty gross, right? I've got a product, and I've got this exponent, and it's like kind of messy. So what we typically do for likelihood estimation is we maximize the log likelihood. So I take log of this. Log's a monotonically increasing function. So the point that maximizes the log likelihood will also maximize the likelihood. Does everyone buy that? All right. So I get this guy. And now what I want to do is get it into this nice form so that I can take a derivative, set it to 0, and get my maximum. OK, so next slide is just going to be kind of some equations. They're just algebra, algebra, algebra calculus, right? So I start with my log likelihood function, just expanding what's going on in there nicely, so that when I take my partial derivative with respect to mu, it's clear what my answer is. So what's the maximum likelihood estimate for mu? Anyone? If you don't raise your hand, I can't call on you.
The average of data points?
That's right. It's the sample mean. Thank goodness we are not crazy. So as an exercise, it would be good if some of you feel like this was kind of rough doing this derivation. A good exercise would be to try and do this for sigma, right? The process would be exactly the same. It's just that at this point, maybe you wouldn't bother with all this algebra. But at this point, you would just take the derivative with respect to sigma and set that to 0, right? So spoiler alert, sigma is going to be the square root of the sample variance. But you should try that at home if this is not review for you and you feel kind of shaky on it. So is everyone good on this right now? OK, great. So for naive Bayes, for continuous data points like those, we often want to estimate a Gaussian. So our class conditional probability is actually equivalent, those of you who have started the homework have already realized this, to a probability parameterized by class conditional means and variances. So what we're learning are actually means and variances associated with Gaussians belonging to particular classes. So this gives us this kind of PDF. So if you want to learn a Gaussian naive Bayes classifier, skipping ahead, all you got to do is apply the MLE that we just did to find these means and variances. Is that clear? Some of you have already, if you've done the problem, the programming problem, you'll have already noticed that this is the case. OK. So if we're all good on maximum likelihood, let's talk about maximum a posteriori, which maybe some of you are less familiar with. Unclear. Oh. OK, why would we actually, first of all, what's the difference between map and MLE? You guys know this. Right, prior. OK, I'm including a prior in my calculation. Why would I do that?
Because we set the data as
Yeah, my data is insufficient in some way, right? Anything else?
If you have a strong prior?
Yeah, you're right. If I believe something to be true, if I have a prior personally, or the hypothesis I'm testing has to do with this prior. There's a third reason why you might want to have a prior, and already kind of touched on it yesterday. Anyone want to? Pardon?
Regularization.
Yeah, regularization. So backing up from that kind of terminology, the principle of regularization and the principle of using a prior is in many ways linked to Occam's razor, which is that your simplest choice is often the correct one. Or in the absence of sufficient information, you should go with the simplest solution. This is Occam. He is a really good stink eye. So we're going to get into that when I go through the example for logistic regression. But keep in the back of your mind that sometimes including a prior will make my solution simpler and therefore potentially better. So the Gaussian example that we just did in MLE, it's pretty simple to extend it to a map kind of problem, right? So I have my density function, and then I say, okay, I have this additional assumption that mu is also drawn from some probability distribution. All I have to do is modify what I'm maxing over. It's pretty simple. And the procedure is exactly the same. So now for logistic regression, which we went over yesterday in class, right? Recall that we were doing this maximum conditional likelihood estimation. So you have these d-dimensional data points, and you're looking at the conditional likelihood, conditional log likelihood, because exponents are gross. And this gave us this big function, and we couldn't really set it to 0 and solve for our weights. But we could go through gradient ascent and then get to a solution. But what's the problem with this? So the problem is that it's under-constrained, right? The solution space for W's is potentially pretty large because I stop the gradient ascent whenever I want to. I don't actually know the truth. I don't know when to stop it. I could just keep going forever. So this is where the Occam's razor side of map estimation comes in. So we want to constrain our parameter space so this solution is hopefully simpler and potentially better. So what we do is we say something like, I think my weight vector comes from this zero mean Gaussian with some covariance. We're just going to call the covariance lambda for now. So my conditional likelihood just has this prior on it. And when you do all the math, which you might want to go through on your own, unclear. When you do all the math, you get this extra term right here. So what is this term doing? If I do a gradient ascent on this function as opposed to the one that didn't have this term in it, what's the difference? And have smaller weights. That's right. So this prior is biasing my weights to be close to 0. Does anyone feel like that could be a bad thing? If you do it too much. If you do it too much. So what's controlling how much I do it? Lambda, right? OK, good. I think you guys probably already know about regularization. But we'll get there in more detail later in the course. So the idea of biasing your parameter space in machine learning is typically called regularization. And in what I just showed you is what we would call ridge regularization or L2 regularization. And it's just, I'm pretty sure you'll prove this in a homework, it's just a zero mean Gaussian prior on your parameters. So why should we regularize? Right? We just realized that you know, this solution space is enormous, and we could get anything potentially. So we bias the weights to be small. And if we do it too much, it might be a bad thing. But why might it be a good thing? Anyone? Just say a random thought.
Because if you increase the number, well, if you have a lot of weights, then sometimes they'll be jumping around all over the place, and if you regularize, then it keeps them from jumping around.
That's very good intuition. So what he said was that if you have many, many weights, there's a potential for there to be noise in your weight estimations, right? They jump around a lot. And if you bias them to be small, then you could potentially save yourself from that horrible, horrible fate. So recall the logistic function. Let's just pretend we've got this like one-dimensional variable, x, and we've got our weight, just one weight, w. Here's a little plot of this for two different kinds of w. So which curve, the red one or the blue one, is the small w, the smaller of the two? It is in the slides, but pardon? The red one, the red one. Okay, so the blue guy, the steeper guy, is the large w. So if w is small, that means my sigmoid is flatter. Why is that a good thing? If this is kind of my decision boundary, why might I want to be less sure about my decision boundary?
So you have a lower probability in this classification.
So do I might have a lower probability for misclassification. But I also I'm risking having a higher probability too, right? Because I'm giving more weight. Basically, if this guy's correct, then he's going to do better, right? If this is the correct boundary. So I'm sort of hedging my bets, right? I'm saying that maybe I'll do better. But why might it be better to be less sure? Right? Like why do you think it would lower the risk of misclassification to smooth this out?
For samples lie like pretty close to the decision boundary.
Right. For samples close to the decision boundary, let's take, like if I take this point right here and I wiggle it just a teeny bit, right? Suddenly its class is going to completely flip. So the noise in my data set is going to affect how well this performs. And if I have a very noisy data set, like how confident am I really that I can be sure at the boundary if things are so jittery? So the point of regularization is kind of you giving a slight vote of no confidence to your features, right? And what we're controlling for is the variance, right? The variance of your classification. And this is something that we're going to talk about in great detail, how sometimes kind of having a ostensibly dumber, less sure classifier can be better for you because it's simpler and it's less susceptible to noise in your data set. Does that make sense to everybody? It's kind of a hard thing to wrap your head around. Okay.
We're in a situation where you still have to pick either it is in this class or it's not in this class.
That's right.
Back to the prediction. So if we're talking about one dimension, what difference does it make if we make our prediction less sure? It's like if it's, just a little bit past the boundary, we still have to predict that it is or isn't in that class, right?
So it's true. In one dimension, it's hard to kind of see why regularization helps. And this is getting back to what someone back there said earlier. What it's trying to get at is that if I have a ton of noise, then by being less sure, I'm hedging my bets on that noise. So what I'm trying to say is that if something is slightly off just by noise, I would do a better job if my classifier classified it, right? Like if this guy's just slightly off here, it's much better for me to have the red guy. But in a big multi-dimensional space, that situation becomes much more likely. So if I have this gigantic, d-dimensional space and I'm trying to draw a hyperplane through my data set, which is what we would be doing with this d-dimensional logistic regression. And I have like some points that are just kind of noise along the boundary. What I want is a boundary that doesn't fall for that noise. I think what I should do is maybe draw this on the board so you can see the kind of situation that I'm describing in 2 dimensions. Do you think this board is okay for you guys to view, like if I push it up when I'm done drawing? Okay, great. So I have some plane. I've got my x's, right? This is like class 1 or something. I've got my O's. Notice that they're like not really linearly separable. Like what's the line I want to draw? Do I want to break my back trying to deal with this random O that's super far to the left? Or do I want to draw a line that gets most of them right and disregards that guy as an outlier? Like, what do you think is the better solution? Just like instinctively, right? Like I know it's like instinctive to want to get all of your training points correct, right? It's like if our classifier can't separate all of our training points with these tiny weights, then why would that be a good thing? It's because your test set, which is what you actually care about, is going to come from these data distributions and will likely not be outliers, right? An outlier is just like this one-off thing. So the point, and it's hard to see in this one-dimensional example, the point is that by biasing my weights to be small, I don't let one noisy thing derail them. I don't let them feel too confident about any one data point. We can't trust this O, right? We can't trust him too much. So this gets back to what happens if you regularize too much, right? We talked about what affects how much I'm regularizing, and it's this lambda. And a lot of you knew that, right? So how do I pick a lambda? Those of you that knew right away what it was can probably tell me. How do I choose how much to regularize? What was it? Cross-validation. Does everyone know what that means? Seeing some blank faces. Yeah, that's good, because that's what this class is supposed to teach. So generally what I would do when I'm training a classifier that has something like a lambda in it, which we would call a hyperparameter, right? It's not a learned parameter like W. It's this other random thing that I have to decide on, is that I take some of my data set and I put it aside, some of my training data. And then I learn a bunch of W's using some lambda value. And then I evaluate how well I did on that held out set. And I can do this over and over again until every data point has been in the held out set at least once. And I can do this for all possible lambdas. And then I pick the one that optimizes the cross-validation error. So you see how now my choice of what to draw is impacted by how well I think I'll perform on a test data set. Most of the time, my test data points are going to be over here, if they're from the O class. Most of the time, from the X class, they'll be over here. So it'll become clear that I want a line that's like, kind of like that, right? Not as curvy, obviously, but a line that's kind of like this, that gets most of them right, but isn't swayed by the outlier point. Does that clarify what you were asking? Sort of? Okay. We can talk after also. So who's not convinced by this? Anyone feel like there's a problem with what I just said? Anyone still feel like I should draw this point, draw this line, such that I classify all my training points correctly? It's reasonable to feel that way, because we haven't gotten into bias and variance yet. But the point is that maximum posteriori reasoning, estimation, allows me to control my solution space in a way that is potentially helpful, or at the very least, optimizable for the performance that I want to achieve. And this gives rise to the principle of regularization. Are there more questions on this? Because went really fast. And
So does regularization change the decision boundary, or does it change these sides of the...
It does. Regularization is changing the W that I learn, right? Because when I'm doing my gradient ascent, the gradient I'm traveling along is now different. I'm optimizing like a totally different function, right? And it's still concave, and I can still find a maximum, but it's not going to be the same maximum as when I didn't have that term. So I have changed the boundary. I've changed it to be less steep in the case of logistic regression. Did that answer okay? Okay. Are there more questions? Because we can spend the rest of the time working out your questions.
So just so I understand your notation, so the weight vector is itself normally distributed? That's what this is saying up there.
It's saying that I suppose it to be.
You're supposing it to be.
I'm supposing it to be drawn from a zero mean Gaussian.
Okay. And it's the parameter of our probability function there, right? Why are we multiplying it? Why are we multiplying that by the probability of W? Like, can you explain what that means exactly? What the probability of W means?
Yeah, it's easier if we go back a slide. Or 2 slides, I guess. Yeah. Okay. So maximum likelihood is just maximizing the likelihood function, right? What I want to do in maximum a posteriori is maximize the posterior as a unit. So if you recall from Bayes' rule, I don't have room on this board. Okay, well, can you guys see if I write it right here? Should I erase? Or should I go out here? This is fine? People on that end, that's okay? Okay, great. So I've got my Bayes' rule, P of y given x equals my, actually we can just not worry about the normalizing term, is proportional to, right, P of x given y, P of y. Oh, I wrote into my little thing. Okay, so the pieces of this, right, this is the conditional probability of interest that we're looking for. And we get at it by looking at the likelihood and the prior. And the product of the likelihood and the prior gives us the posterior. So maximum a posteriori, normally like in maximum likelihood estimation, we assume that this is some constant that doesn't affect our parameter estimation. right? We only worry about maximizing the likelihood because that's the only thing that contains the thing we're maximizing over, right? But now what I'm saying is the prior matters. The prior matters to me, and so I need to include it in the function that I'm maximizing over. So that's how you go from your MLE to your map. And so it's easier to see here. Originally, in the MLE sample example, we just maximized this, right? Without anything else. But now I'm saying, okay, I have more than just a uniform prior over mu, right? I have some actual idea about what mu might be for whatever reason. So I multiply it in, and I do the maximization as I normally would.
So is this still an application of Bayes' rule?
Yes.
Okay, so this is like the probability of x given parameters mu and sigma times the probability that mu is some particular.
Yes.
Right.
That's exactly what it is. Is everyone okay with that notation? Like usually you would do the vertical bar for other random variables and the semicolon to indicate parameters. I hope that didn't, it's just the way. No. Okay. So then is it clear then why we do this here? Why we multiply by the weight?
Yeah, that's just
Yeah.
That makes sense.
Okay, great. Anything else? Anything at all? I don't know. Some people look puzzled and some people are like, okay, we're done.
I don't get how this helps if you have insufficient data.
So you're right. Regularization, it's not really a cure for insufficient data. I mean, nothing is like a super cure. So an example that I don't have in this slide because in the slide deck because Artie kind of went through it in class is recall in discrete naive Bayes. I'm just ignore the distracting moving through the slides. In discrete naive Bayes, right, we were getting these probability counts. This is how we were estimating our parameters, right? We were like, okay, how many times does this occur in the data set? And this is going to give me my probability. So if I don't have that much data, then some of these numbers are going to be 0. And 0 probabilities, generally terrible. Do not want those. And will mess up my naive Bayes classifier pretty badly. So typically what you would do is put a prior that everything occurs at least once, kind of. It's called Laplace smoothing. Maybe I'll write it down if you want to look it up later. So when you do this kind of smoothing, instead of doing the maximum likelihood estimate for your discrete Bayes classifier, you're now doing maximum a posteriori because you've included a prior that puts some weight on every possible feature. Okay? So that's how it can help with insufficient data.
Example like you gave on the board where the data isn't nearly separable, you don't really have the option of like overfitting to the data. So what does regularization do in those kind of cases where you have an inherent misclassification rate?
Well, if you have an inherent misclassification rate, you do, so you always risk overfitting to the data, right? Even if they're not perfectly linearly separable. It's just that it's a question of like how bad is overfitting versus underfitting in that case, right? I think this is what you're getting at. Generally, regularization will cause you to underfit. But if you modulate how much you regularize by your cross-validation error, then hopefully you're fitting just the right amount to control the potential test error, right? Because the goal of learning these classifiers is not to do well on the training set, which you already know the labels for. The goal is to generalize to something you've never seen before. Does that make sense? Okay.
So if your data was representative of the population you're assuming, would the map and the MLE be
If your prior was the truth, well, so MLE is in some ways assuming a uniform kind of prior. So if the true prior is not uniform, and you somehow hit upon it with map, then map will do better.
So I thought MLE is actually assuming a fixed value of parameter. So we don't have a prior. So it's basically a frequency to view. So you don't actually have a prior on the parameter because it's considered to be fixed. And the map is basically you assume there's a prior, that there's a distribution on the parameter.
Right, right.
So
that's a better way to answer that question.
because if it's uniform prior, then that's not 1, right? Because it's uniform from a range. Okay, from 1 to 10, then the probability is
Right,
1 to
right.
10.
Right. Okay, that's a much better answer. So to explain what he said, is that in maximum likelihood estimation, we assume that the prior doesn't affect our estimate of the parameter because it's not a random variable. So if it's not a random variable and it's fixed, then assuming a distribution for it is going to mess you up. But if it does come from a particular distribution, and you guess that distribution right for your map estimate, then map will win. Okay.
Yeah, so it seems like you sort of mentioned that regularization is one of the techniques you use to deal with insufficient data, but it seems like it's also a big factor has to do with the number of like features or dimension of the training data. So like you could have a lot of data, but if you have a lot of features, that seems like a situation where regularization probably helps you more, right?
That's right. That's correct. So that is another way that having a prior helps with insufficient data. In general, when you have more features than instances, you have a very under-constrained problem. And that's when you want to bias your solution space to something that you think is likely. So if you can imagine, try to imagine, if I have this like 3-dimensional space, but I only have 2 points in it, it's very hard for me to have enough information from just those 2 points to draw a reasonable boundary. I mean, that's like a kind of silly toy example, but if I had like this million dimensional space and I only had 100 points, how could I possibly capture enough information about that million-dimensional space in these 100 points to draw a reasonable line? So regularization can save you from doing something crazy when you have many more features than instances. I'm trying to think of a good example of this. Like if you think of it from a linear algebra perspective, right? What happens if a matrix is super duper fat? It's got many more columns than rows. What's its rank going to be? Number of rows, right? The rank's going to be small. But what I care about is its columns. This is kind of what we get at. Is that if I think about rows as being samples and columns as being features, I can only capture as much information as I have rows in that situation. So regularization is kind of like saying, okay, well, you only have this much information to work with, but we have a supposition or we have additional information that should help you out. Does that help? I wasn't sure about how your linear algebra is, but when we get into regression, more generally linear regression, you're going to see this in action. More questions?
So is it possible to use error norm for the regularization?
Yeah, right. So that's a good question. What prior do you think an L1 norm is equivalent to, right? If what I call L2 regression, sorry, I'm just gonna scroll all the way there. So if L2 regularization gives me, is drawn from this zero mean Gaussian prior, what do you think the L1 penalty that you're asking me about comes from? It's okay if you don't know. It's a Laplace distribution, right? Yeah. So we're going to get into that more when we do regularization. I don't want to kind of get into L1 penalties and the lasso right now. But we can also talk after if you want. But I think what your question reveals is that this prior is going to change this penalty in different ways, and it's going to have different effects on how we can optimize this function. So the world of regularization is pretty interesting. No, not this one, right? Like the problem is like this term, right? This log of the 1 plus x, but you can't really compute a closed form. There are many things you can compute a closed form for, right? When you want to estimate, do like a linear regression estimate instead of this logistic one. But the nice thing, the properties of this regularizer matter, right? Because we want to still have a concave function after we add it in, so that we know that if we found a local maximum, it's the global maximum. And it would be nice if it were smooth and differentiable too, but that's not totally necessary. There are optimization techniques to deal with this regularization term not being smooth or differentiable at some point. More questions?
Why is the summation from 1 to d instead of 0 to d?
That's just my habit because I use MATLAB. I have d features, so I sum over them. So w is a vector in Rd.
Yeah, but I mean the parameters include w0.
Oh, okay, that's a typo. Yeah, that should go from 0 to d. I'll fix that and post a new version. Although some people would argue that you don't want to include W0 in here, but that's kind of a big subtlety that I think is out of the scope of this course because people still haven't agreed on an answer. But when I run this, I actually don't include W0 in that term. But that's a good point that you brought up. More questions about this, about anything at all?
We talked about the, if you break the class conditional assumption, so if like two features are correlated exactly, how does that affect the P of y and x?
Are you okay. So Artie kind of mentioned this in class, right? If two features are intensely correlated, it's going to bias your conditional probability, right? Do you feel like you know which direction it would bias it in? If I had two features, so let's say, blah, blah, blah. Let's say I was doing some kind of bizarre classification where my features were things like, I had something that was like sunny, and then I had some like Boolean feature like rainy, right? Those two things don't really happen at the same time, do they? Maybe they do, I don't know. But, right, and what I care about is like picnic spots, I think is her example, right? So the probability, so this is like weather 1 and weather 2, and these are just like Boolean guys, either they're true or false, right? So the probability of like a good picnic spot given weather 1 and weather 2, if these are perfectly anti-correlated, what do you think that's going to be biased to be? If you can you see this board? Maybe I can, goodbye other board. Okay. Can you see this, everybody, or is it blocked by the screen? Okay. Does anyone have an answer? I'm pretty sure this is an online question, so you're all going to have answers.
Did she say that it biased, like, you were looking 72 times?
Pardon?
Didn't already say that it was as if you kind of signed twice?
That's right. That's right. It's going to be as if Sunny came up twice. So, but what does that mean for my classification?
Too much importance to that.
That's right. That's right. So if you guys can't hear him, he said that given that we're now counting Sunny effectively twice, we're going to give too much importance to this parameter. And so our classification is going to be biased, kind of however our training set is biased by the presence of Sunny. Does that make sense? Person who asked this question?
So it would be biased towards the probability of days that are sunny.
That's right.
Can I go back to your slide?
Yeah.
So, why after add the prior to the likelihood, then we can get the equation that just minus the sigma, the number.
Pardon? Because I took the log likelihood.
Yes.
So this P of W can just come out of this product, right? It's not affected by J. So I get log of P of W here, right? But W comes from a zero mean, like 1 over lambda Gaussian. So if I just like go through the math of just having this PDF, like we're called a Gaussian PDF, is that? I think that might be, okay, that's a little far back. But if it's zero mean, and I take the log, and it will all collapse to this, the other terms will drop out. Does that make sense? It's just like an algebraic log rule kind of a deal.
The Gaussian is minus x squared by 2 sigma squared. So if you take natural, you should get minus.
Yeah. Oh, I see. That was the question, was why is it minus? That's right. Because there's a minus on the interior. Other questions?
So I guess I'm still not, so you said it was biased towards the probability that it's sunny. What if the probability that it's random day is sunny is like 60% of days are sunny? So that wouldn't necessarily be going to 0 or 1. The way I'm saying it.
You mean this wouldn't necessarily be going to 0 or 1? So because that's an online question, I really don't want to like get into its answer too much. But if somebody wants to help this guy out or think out loud, that's okay with me. Anyone? Okay, well, I think, yeah.
We're giving too much importance to the, because rainy is kind of stating sunny or not again. So we're giving too much importance to sunny. So the weight on sunny will be, we'll bias our answer too much on whether the day is sunny or not. So if our training data has a lot of sunny days that are good, we'll be biased towards that answer. It depends on our training data.
Do you want me to repeat what he said? So what he said is that if I have a lot of sunny days, and sunny is a good predictor that it's going to be a good picnic day, then it's effectively saying that Sunny is twice as powerful. So any instance of Sunny in my training set is going to be super powerful. So if the majority of my training samples have sunny days leading to good picnic spots, then I will go with the majority vote.
But it's not just the training data, right? It's like if the distribution of the actual true sample, but all of this violates the conditional assumption, then you'll have this bias. Yeah, like I said, and that will determine what your training data is probably. But just in general, violate the conditional assumption.
Sorry, could you say that more loudly, please?
Oh, I'm saying that just violating the conditional assumption is the issue here. It's not whether or not you're looking at just your test data or your training data. It's that there's a violation of the conditional assumption.
Right.
Violation will lead to giving too much importance to the fact that they.
Yeah, when they're correlated, you're basically double counting.
Right. So that question is about the extreme case of perfect correlation. But you're correct that any kind of relationship, even if it's not as strong as this one, is going to bias your solution. Does that make you, is that better? Or okay.
Like sunny means it's a good picnic spot. That's the thing
Oh, I see. Right. Sorry, I was referencing, I think, like 3 lectures ago or something. Okay. Are there more questions on this or on anything at all? Does everyone feel okay about bag of words? Because I know there's a few questions on that.
You really just take the set of words and discount multiple occurrences.
Right, you take the unique set of words. Throw them in a bag, you don't care about them. You can do pretty good stuff with that, actually. Like, it seems kind of silly, but, you know, the words in a paper about molecular biology are super different from the words in a paper about economics. So you can do some, it's disregarding grammar is not actually that detrimental to many classification tasks of interest.
So isn't bag of words prone to correlation more? Like if I see a word like bark in my bag of words, I'm almost obviously going to see a word like dog. So that's going to be pretty much correlated.
So what you're saying is that bag of words in some ways captures co-occurrence statistics.
Yeah.
That's true. It captures document level co-occurrence statistics. It doesn't capture like the sentence level at all. And so what a lot of people find useful, more useful to use, would be a sentence level co-occurrence. So dog barked, that correlates in sentences as well as in documents. But it doesn't really, they don't really co-occur, like bark and veterinarian don't really co-occur in the same sentence, but they might occur in the same document. So there's many levels of co-occurrence. And if you're interested in this, I think LTI offers probably all the classes in the universe on it. Okay. Yeah.
I have another question about PFW.
Okay.
It says that W is normally distributed. Could you expand on, like, is a PFW less than some value of W? Are we talking about a CDF?
No, I'm talking about the PDF.
Okay, that's the PFW right there is the PDF.
Yes. Yeah. But the variance of W is contained by lambda. So in that sense, the size of W is contained, but it's not. This is like just multiplying probabilities.
By the way, you said we could take out PFW out of the product and read it's not dependent on J, but isn't there a power event that affects it?
Yeah.
So there's like a lambda n sum of the W.
I don't think so. I think that the n got taken out from everything. I don't think so, but I don't have the thing I did it on me. But generally, when you optimize this, there's no n term anywhere except on your data. Right, because it's kind of like this product is only affecting that term. So I guess I wrote it kind of in a misleading way. But like if you think, here, let me, because it's like this product is because these data points are IID. So what I actually want to do, right, okay. Does that make sense? Sorry, I should have put brackets. Does everyone understand why P of W can be taken out of the product, or should I go through that more slowly? Because you kind of figured it out while I was saying it. Does anyone not understand? Okay. Great. Yeah, so the key assumption that we used here, though, is that our data points are IID. And it would be terrible if they were not, basically. Any other questions? Anything at all? Okay. So just a quick recap then, if there are no more questions. No, you guys always have a question right when I'm about to go to the last bit. Okay. So we went over this bag of words, and everyone feels good about that. And we went through the MLE derivation. Do you all feel like you could go through the derivation for sigma / you have in some other course, maybe? Okay. Well, all the equations are there. The slides are posted. And we went over maximum a posteriori, which is using a prior to bias our parameter estimates. But the actual math of the situation doesn't really change. It's just that the function we're maximizing has gotten a little more complicated because we've added this prior in. Okay, so if everybody's good, then we can call it a day.